All right, Titans, welcome back to episode 2, Algebra 2, Flipping the Classroom. We're going to talk about permutations this afternoon, tonight, this morning, whatever it is when you're watching this. Permutations, we're thinking about order. So basically, we're thinking about if we're going to go to the lunch line, how many different ways can we stand in line? There's an order to that. It matters what order we stand. How many different ways can we finish a race? We can finish first, second, third. Well, how many different ways can we finish that? There's an order to it. So an ordering of n objects is a permutation of the objects. Let's go. There are 6 permutations. If we look at the letters A, B, C, how many different ways can I order A, B, C? Well, basically A, B, C, ACB, BAC, BCA, CAB, or CBA. Those are the only 6. And one way I could do this, instead of writing them all out, is I can actually use the fundamental counting principle. Basically, there's 3 choices for that first letter. A, B, or C. If I pick A, now there's only B or C for the second one. If I pick C, there's only A or B for the second one. And then the third one, it comes down to just one choice. So I've got 3 choices for the first one, 2 choices for the second, 1 choice for the third. What am I doing there? Taking 3 times 2 times 1. My choices. I've got 3 spots, 3 times 2 times 1. So there's 6 ways to arrange the letters, which I found by writing all those out. Using the fundamental counting principle, and what else we're going to learn here about permutations, we'll just make this simpler instead of writing these out. In general, the number of permutations of n objects is what we call n factorial. Something new here. This factorial sign this exclamation point stands for factorial, which is n times n minus 1 times n minus 2. Right now you might be thinking, what does that mean? Here's your example. 4 factorial. All that means is I'm going to take 4 times 3 times 2 times 1. All the numbers smaller than it, all the way down to 1. And 4 times 3 times 2 times 1 is 24. If I had 5 factorial, I'm just going to take 5 times 4 times 3 times 2 all the way down to 1. Multiply those together, you get 120. So we can use a factorial to help solve these as well. If I did 9 factorial, it'd be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So that is our factorials. Okay? Something new, factorial. Make sure you know it. Looking here, in how many different ways can 8 skiers in the Olympic finals finish the competition if there are no ties? So they can't finish like 2 people finish first, 3 people finish 5th. They got to finish in an order. Well, how many ways can they? If there's 8 skiers, there's 8 spots. So what I come up with is 8 different spots, and only one can finish first, so there's 8 different choices for that. 8. If one finishes first, they can't finish second, so then there's 7. 6, 5, 4, 3, 2, and all the way down to 1, which is just 8 factorial, or 40,320 different ways. Crazy. Crazy to think they could finish that many different ways. Okay? Look at this next one. How many different ways can 3 of the skiers finish first, second, and third? So same problem. You got 8 skiers. I'm not looking at how many different ways they can all finish the race. Only how many different ways can they get gold, silver, and bronze. Well, now I kind of use that fundamental counting principle. How many spots do I have? I've got 3. And any of the 8 skiers can finish first. Then any of the remaining 7 can finish second. Any of the remaining 6 can finish third. So really I've only got 3 spots here, which is 8, 7, and 6. So 3 spots, 8 people can finish first, 7 second, 6 third, which leaves me with 336. Okay? And that brings up the next thing, that we didn't use a factorial there. Instead what we use is what we call n choose r. N choose r, and this is a good formula here. N choose r, or n permutations of r. And it's n factorial over n minus r factorial. And this is what we call permutation form. So some examples might be like 12, and we say choose. Instead of that p, we say choose 5. Or 8 choose 3. Or 7, choose 2. That's all that is. Okay? Permutation, notation. Permutation, notation. 12, choose 5. 8, choose 3. And what I would do is I would just plug those in. N gets plugged into the formula. R gets plugged into the formula. So now using this, let's look back at that last problem. We can set that up as the number of 8 objects taken 3 at a time. Because I've got 8 skiers, I only want to know about 3 of them. So it's 8, choose 3. And again, using this formula, 8 gets plugged in for n, 3 gets plugged in for r. So I get 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial. And 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. 5 factorial, 5, 4, 3, 2, 1. We can multiply these. And you can multiply those numbers all the way out. Or, check this out, I could cross out whatever I have on top of a fraction and on bottom, cancel out just to 1. Well, that just leaves me with 8, 7, and 6. And 8 times 7 times 6 we already know was 336. So again, a couple different ways you could do that. Just the fundamental counting principle, or actually using this formula. Okay? That is for permutations again. Permutations. So here, let's look at this one. 10 colleges. You want to visit all or some of them. Got 10 colleges, and I want to visit all or some of them. How many ways can you visit 6 of them? Well, that'd be a permutation of 10 objects taken 6 at a time. So 10p, or 10 choose 6. 10 choose 6. And we'll walk through this here. 10 choose 6 using that formula is 10 factorial over 10 minus 6 factorial, which is 10 factorial over 4 factorial. 10 factorial is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 4 factorial is 4, 3, 2, 1. This time I'm going ahead and multiplied all those out. So those top numbers multiplied out are 3,628,800. 4 times 3 times 2 times 1 is 24. Just divided those, and I get 151,200. So just using our formula there. 10 colleges, I'm going to visit 6 of them. 10 choose 6. 10 choose 6. Now, you looking at that same problem, what would be an easier way? Well, I'm going to kind of use the fundamental counting principle. Whenever I have a permutation, I'm thinking, again, 10 choose 6. But the way I think it is, I've got 6 choices, that second number, so I make out my 6 spots. And this first number is kind of where I start. So I start at 10, then work my way down. 9, 8, 7, 6, and 5. I start at 10, work my way down. I don't go all the way down to 1 this time because I only had 6 spots, which was from that second number. This is kind of my shortcut. The second number tells you how many spots. The first number tells you where to start. And 10 times 9 times 8 times 7 times 6 times 5 is 151,200, which is the same as the number I got on the one before using the formula. But I got a lot bigger numbers that I had to deal with. This is just kind of a shortcut. Second number, number of spots. First number, number you start with, and then start going down by 1. Okay, that's my shortcut. You can use either method. Again, rewind this, fast forward, pause it, do what you got to do, see what we got going here. Okay? All right. How many ways can you visit all 10 of them? Well, if I wanted to visit all 10, I'd have 10 choose 10, which would be 10 factorial over 10 minus 10 factorial. Well, that brings up a special point here, and I could make 10 spots and then start at 10, which is just 10 factorial. Or let's look at this. What is 10 minus 10 factorial? That's 0 factorial. And you might want to just write in your notes somewhere, 0 factorial equals 1. 0 factorial equals 1. That is very important. You can't really do 0 down to 1 like normal factorials. So 0 factorial equals 1 is huge. Okay? So it's 10 factorial over 1, which is 3,628,800. Okay, got something new there, 0 factorial. Moving on. So far we've just used distinct objects. You know, I have different racers, I have different colleges. Well, what happens if some of the objects are repeated? Then some of the permutations are not distinguishable. So let's look at the letters in MOM, M-O-M. Basically in MOM you have 2 M's. Well, in this first one and second one, these are really the same. These are really the same. And these are really the same. Because the M's, if I don't label them 1 and 2, they're just the same letter. So if those are the same, I really only got 3 spots. And how I do that is I take 3 factorial over 2 factorial. What does that mean? Well, here we go. The number of distinguishable permutations of n objects, where one object is repeated q1 times, another is repeated q2 times, and so on. So you take the number total, factorial, divided by however many times it repeats. What's that mean? Let's look at an answer here. Ohio, 4 letters, zeros repeated twice. So on top I have 4 factorial, zeros repeated, or O I guess, is repeated twice. So 2 factorial goes on the bottom. 4 factorial is 24, 2 factorial is 2. 24 divided by 2 is 12. So there's 12 distinguishable permutations here. Mississippi. Mississippi has 11 letters. I repeats 4 times, S 4 times, P 2 times. So on top, your N is your total number of letters, which is 11 factorial. Then your number of repeats on the bottom, 4 factorial, and 2 factorial. 39,916,800 divided by 24 times 24 times 24. Use your calculator there. You get 34,650. What does this mean? If I was to rearrange those letters in Mississippi, I could do it 34,650 different times. Pretty awesome. Here's 2 problems for you getting down to the very end here. Go ahead, pause this, see if you can solve these. Alright, coming back here. Find the number of distinguishable permutations of the letters. Well, summer, how many letters are there? 2, 4, 6. So 6 factorial goes on the top. What's repeated? M is repeated twice, so 2 factorial goes on the bottom. I'd go ahead and solve that, and you should have come up with 360. Waterfall has 2, 4, 6, 8, and 9 letters, which is 9 factorial. What's repeated? There's an A twice, so I put 2 factorial on the bottom. There's an L twice, so I put 2 factorial on the bottom. And I think that's it. So this is 9 factorial over 2 factorial times 2 factorial. And you should have came out with 90,720 as your answer. Alright. Number of permutations. How many different ways could I rearrange those? Last one here. A dog has 8 puppies, 3 male and 5 female. How many birth orders are possible? If you want to go ahead and try this on your own, pause it right now. If not, here we go. Well, how many puppies are there? There's 8, so 8 factorial. Oh, I went one too fast there, sorry. Going back real quick here. Eight puppies, so there's 8 total. That goes on top. How many repeats are there? Well, there's 3 males. That goes on bottom. Then there's 5 females, so that goes on bottom. I take 8 factorial over 3 factorial times 5 factorial. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. And 5 times 4 times 3 times 2 times 1. Well, I know that some of these are going to cancel out. 5s, my 4s, my 3s, my 2s, my 1s. 3 times 2, that adds up or multiplies to 6. So really all I have is 8 times 7 there, so there's 56 different ways they could come out. Lots of multiplying here. And that is all she wrote for this episode. End of episode 2. We'll get back after it in class. Make sure you've watched this right at 15 minutes. Hopefully you stuck with me, and we'll see you in class. Later, Titans.